All right, so the next we're gonna look at projectile motion, which is basically a two-dimensional free fall. So you can have like a baseball, tennis ball, right? Olympic driver, all exhibit projectile motion. Because let's say object that is moving due to the influence of gravity, right? And exhibit this type of motion. We first looked at one-dimensional free fall, where the object goes straight up or the straight down. But every time, let's say it's not straight up or straight down, but still moving under the influence of gravity, then generally, you can call this as a projectile. So the projectile is an object that moves in two dimensions under the influence of only gravity, nothing else. And we are obviously, simplifying it a little bit, because there is no such thing as motion only due to gravity unless it's vacuum. So we are always then assuming that the air resistance, you can see, right, is negligible. So if you can ignore air resistance, then technically we can assume again that object is, exhibits free fall. The difference here is that in a previous chapter, right, chapter 2, when we talk about, one-dimensional free fall, we assume that object only going up or down, that means there's only vertical, let's say velocity, and there's only vertical position change and things like that. But here then we can see that as object basically, instead of going straight up or straight down, can technically move like this and then go, let's say if it's given some kind of initial velocity like that, can exhibit motion like this. Or if you have a soccer ball and you kick it like this, it can actually go like that. That means there could be like some kind of parabolic trajectory, which you can see in the picture of a tennis ball, right? Because the ball's trajectory between bounces is a parabola, which means that technically motion due to, let's say due to the gravity, right? This projectile motion can be modeled as a parabola. All right, so generally this projectile problems fall into two categories. One with some kind of non-zero launch angle, okay? That means things like this. You have a ball, right, sitting here, and then you give it a kick, right? And the ball moves with this velocity, right? So moves such that, remember, this is vertical versus horizontal, axis. It means it's not a time, time dependent, let's say, graph. So it just basically, it gives you actual trajectory. So at the instant when it's sitting there at t equals 0, right, and the origin, you give it a kick, that's the direction of the velocity. It means that's the direction of the kick that you give, and it's going to be moving initially like that. But then the gravity takes over, and the object kind of slows down, kind of like more, and then comes back down. Okay. So that means what we do here, we say there is some kind of launch angle. Okay, so launch angle that is non-zero. And that initial velocity, right, this v initial, is then a two-dimensional velocity vector with launch angle theta initial. Now, what do we do right away with this type of problems? Well, we don't want to work with a two-dimensional vector. So we take them and we break them down into components, where then we look at x component of the initial velocity, which is v naught cosine theta, and x component of the vertical velocity, which is v naught sine of theta. That means right away, we take and break them down into components, x and y component, okay? Where then v initial is the, obviously the initial speed. Now you can think of it like this, right? So this is assuming that you are given v initial and the theta initial, then you use this. But what if you're given components, v naught x and v naught y? What if you're given components? Well, then remember, you can still use them to find the initial velocity with, square of initial x square plus, initial y square, square root of that, to find the speed, initial speed, and find the launch angle, where then we can use inverse tangent of v initial y over v initial x. That means given those, calculate the components, or given components, calculate the speed and direction of your parent initial vector. You can kind of go back and forth, because some problems you can actually solve for the components first and then use that to find, let's say, the magnitude of the initial velocity. All right, so remember that gravity only acting downward, which means that projectile problems are affected only by gravity, and gravity only acting in vertical direction, which means these two things, right, will be always true for the projectile motion. That means acceleration as a vector which instead of axi hat plus ayj hat, will only be in terms of 0 I hat, but negative gj hat. So this is the acceleration of the free fall. Okay, that means there's no horizontal acceleration ever, and negative g acceleration in y direction. All right, so that's why we can then assume that if those things are true, right, then the object here is in free fall in those two states, ax equals 0 and ay equals negative g. Only projectile motion has that. Okay, so that's why it's a free fall, because there's no other things affecting the motion but gravity, and this is the effect only due to gravity. All right. So for example, then, what does it mean in terms of ax equals 0? Let's say in the x direction. Well, it means this. For example, you take this velocity vector initially. So this is that at t equals 0. And we use those two equations, right? We use those equations to find x and y component. V naught x equals V naught cosine theta. And let's say we calculate and we got 9.8 meter per second. All right. So just coincidence that it's just, So then let's say we have V naught y, which is then V naught sine of theta naught, right? Then let's say we got 19.6 meter per second. Those are the x and y component initially. Now, what it means here is this. Since ax equals 0 and ay equals negative g, means that if I look at some later time, during the trajectory, right, during the motion, at some later time, and look at velocity vector, if I break it into components, so let's say 1 second later, so t equals now 1 second. Here is t equals 0 seconds. What it means is this. 1 second later, this is by how much horizontal velocity would change. How much? Well, 0. That means if I break it down into horizontal, I'm going to get the same as before. How about in a vertical direction? Well, whatever you had now should change by exactly that amount, which is negative 9.8. So that's why if I measure the velocity in a y direction, it will be decreased by that much. Why decrease? Because velocity was up, acceleration was down. Opposite direction means that velocity will decrease. So that's why velocity in a y direction is 9.8. Different, it slowed down, but velocity in x direction is the same as before because it didn't change. How about t equals 2 seconds? Well, here's what I have. Well, if you were moving at 9.8 meter per second in a y direction at t equals 1 second, t equals 2 seconds, then it's going to decrease again by exactly this much, 9.8 meter per second downward. That means it will decrease by that much. So if it was already 9.8, now it's going to be decreased by 9.8. So Vy here is 0. How about Vx? Well, it decreased by exactly 0 amount. It means it's exactly the same as before. And you can see, right, x is always exactly same because V naught x is same as Vx at any time and is constant, which means in the x direction, you have a uniform motion. That means the motion never changes its speed or velocity, technically, right? That means there is no acceleration in the x direction. There is no change in velocity in the x direction. It's a uniform velocity or uniform motion, constant velocity. In a y direction, there's a constant acceleration. That means every second your velocity changes by 9.8 in a vertical direction. That means you have to pay attention to, let's say that acceleration in a y direction. So here's then what I have. So let's say in terms of what is the difference between object being dropped or object basically moving in a projectile, two-dimensional free fall. That means comparing one-dimensional versus two-dimensional free fall. Assuming again it's a vacuum, so air resistance is neglected and everything. So think like this: if I take this object, red object, and just drop it, and then I take the yellow and give it some initial velocity in this direction and then have it go at a projectile motion, will they hit the ground at the same time? So generally, this is a question that I ask in my class, and I even do this experiment. It's a very straightforward experiment. I suggest you guys do that. Try that at home. Take 2 pencils, something that you won't break, and then drop them such that you're dropping one and throwing the other one in a horizontal direction, and then try to hear if they hit the ground at the same time or not. All right. If you do that experiment, you should, if the air resistance is negligible, and let's say you're using object that more or less compact and heavy, then they should hit the ground at the same time, okay? Because what I have here is this. See, they start with no initial velocity in a y direction, and this technically also has no initial velocity in a y direction. Because this velocity right now is only horizontal. You give it a horizontal velocity only, so the v initial y is the same. So then when they go and hit the ground, they're gonna hit the ground exactly same time. Right? So this is something that if they start from the same height, they're gonna go and hit the ground exactly same time. Okay. Because remember that equation, right? Delta y is equals to 1/2, at squared, right? If initial velocity is 0. If you have the same delta y and then you have the same a acting on both of them, then the time interval will be basically the same. All right. So the difference here is, if I actually go back here, the difference is that if you're looking at the one-dimensional motion, free fall, it's only moving along the y-axis. But if you're looking at the two-dimensional free fall, then this is being x initial, right? For example, then there's also some kind of x final. So there is a change in x as well as there's a change in y. So that's why in a two-dimensional free fall, you need to take into account both of those motions, how it changes in the x direction, how it changes in the y direction, and kind of combine them together. So that's why generally, if it's it is a two-dimensional motion, but for the projectile, we prefer to separate x and y motion into two independent motions, look at each one independently and then combine them together whenever we need. And remember, one thing that connects them is the time, right? How long does it take to go this displacement is exactly the same as that displacement. Exactly same time interval for both axes. All right, so these are some examples. Let's say, we can write a projectile with initial velocity and has a launch angle of theta above the horizontal. So the question is, how far does it travel over the level ground before it returns to the same elevation from which it was launched? And this is important because if I take this to be point A, and then when it hits the ground as point B, I'm assuming that position of A, vertical position of A and B are the same. Okay, that means I'm talking about same elevation, start and final points. In that case, one thing we can do here is we can combine x and y equations, right? In direction, right, of those equations, and we can combine with some kind of distance equation, which will be v naught squared sine of 2 theta over g. Okay. So you can see, right, example 4.5 from your textbook will show you this. So if you have the textbook, go ahead and look at in terms of this, which means that you can find the distance, horizontal distance, sometimes also known as range. So like let's say R, right, which is the range. And you can see that you can calculate this, and this is sort of like, let's say, only depends on two things: your initial velocity and your launch angle. That's it, nothing else. You can find the range. The only thing here is you have to understand that this is equation that not always works. It only works if it returns to the same elevation. Okay, so let's say if you start from here and then go down, let's say that's not going to work. This is not going to give you the range. If you start from the ground and go something over here, again, it's not going to give you the range, right? Only when you start and come back to the same elevation, then you can use this equation to get the range. Also interesting to see which angle gives you the maximum range if air resistance is negligible. And that's happened to be 45 degrees. For example, here you can see, right, if you shoot the object or, let's say launch the object at 45 degrees, it's going to reach 1,000 meters when every other angle, right, is going to give you a little bit less. Also interesting to see that 15 and 75 gives you the same, and 30 and 60 give you the same. Hopefully you guys can see a pattern. Those are basically complementary angles. So that's why they give you same technically, same distance. All right, so let's then start solving some problems. Okay. Remember when I said that there are technically two categories of the projectile problem. One with some launch angle. We looked at this. But there are also other ones where the launch angle theta is 0. We call it 0 launch angle. And the way this works is basically this. So you are looking at the motion where your launch angle, basically initially 0, which means the object is moving horizontally, then goes into the free fall. Okay. Remember, one thing we're doing here is this. So let's say we are looking at a projectile motion, right? And it's important to understand that what I'm going to do right now, I'm going to show you how I'm separating X and Y axes, independently from one another, look at motion horizontal and vertical separately, and then combining to solve for whatever I need. So let's see what I have. I have a movie stunt driver on a motorcycle, speeds horizontally off a 50-meter high cliff. How fast must the motorcycle leave the cliff top to land on level ground below 90 meters from the base of the cliff where the cameras are? The cameras are somewhere over here, let's say. And we're going to ignore air resistance. Good. That means I can have as a free fall problem. Okay. Now, let's write down what we're given. Okay. So we're given, like in the beginning, it says it's a 50-meter high cliff. Well, it means that I take the object, the starting point of the object to be my origin. That means I can say X initial is same as Y initial is 0 at T initial, which is also 0. Then I have then the ground 50-meter, with respect to the starting point. But because it's below my origin now, I can say then Y final here is then negative 50 meters. X final is actually to the right of my origin, so that's technically then 90 meters. Okay. What else are we given? Well, it doesn't seem like anything else, but remember it's a projectile problem, so AX equals 0, AY equals negative G. Those are also very important things to know. What do we want to find? Well, we want to find how fast it was moving. That means initial velocity, basically. And also very important thing we're given here is this. Theta initial here is 0. Why? Again, because, think like this. This is the cliff. So it is moving with some initial velocity, horizontal. It's moving horizontally, and then here, when it goes off the cliff, it is still moving horizontally only. And then it goes free fall like that. All right. That means theta initial here is 0. So, what does it do then? Now, remember then, I'm going to be separating this into two one-dimensional motions, which means then I'm going to look at in terms of anything X separately from anything Y. Okay, so then here's what I have then. I'm going to use this area to write down that. So let's say I have then X direction. Remember, in X direction, I have this, right? AX equals 0, which means there is no acceleration. Well, if there's no acceleration, that means initial velocity in the X direction is same as final velocity in X direction. That means I have just Vx, and it's constant. Okay, which means that this is uniform motion, right? And that means I have just one equation in X direction, which means delta X, displacement in X direction, is equals to Vx times time. Just this one equation. Well, in a Y direction, I have an acceleration of negative G, but it's also constant. That means I can use those kinematic equations. So that in a Y direction, I actually have all 4 equations that I can use. V final in a Y direction equals V initial in a Y direction minus GT, where again, I'm replacing acceleration with negative G. Equation 2, Y final equals Y initial plus V initial in the Y direction times time minus 1/2 GT square. Equation 3, V final square equals V initial square plus 2 times negative 2G times delta Y. And equation 4, delta Y equals V final Y plus V initial Y divided by 2 times time. That means we can use all of those 4 equations in a Y direction. You can see, right? So everything in this set is in terms of the vertical. Position change, velocities, and acceleration, things like that. Everything here is just in terms of anything X. horizontal displacement, horizontal velocity, and things like that. And again, what connects those two sets, right? Those two, x and y direction, equation set is the time. All right. So then let's, given whatever we have, we can always sort of like, let's say, start the problem by trying to see if we can find the components. Here's what I have. Remember, you take v initial and theta initial and use them to find two things. V initial in the x direction, which is then v initial cosine of theta, in this case 0 degrees. And then v initial in the y direction, which is v initial times sine of the angle, which is in this case 0 degrees. Cosine of 0 gives you 1. That means v initial in the x is equals to v initial. Sine of 0 gives you 0. That means this whole thing is 0, which means there is no initial velocity in the y direction for this problem. And this will be true. When you have zero Lagrange angle problem, your initial velocity in the y direction always going to be 0. That's always going to be true. Okay. But also we have one thing. Remember, we're trying to find initial velocity vector, initial velocity magnitude vector. And here I'm saying that initial velocity is equal to basically my horizontal initial velocity. That means all I have to do here for this problem, find my horizontal initial velocity, then I have my initial velocity vector. Because I'm saying that initial velocity as a vector is equals to vi x I hat plus vi y j hat. But then this is just vi x I hat plus 0 j hat. Means that there is no vertical velocity in the y direction, and vi is just basically equal to the x component of the vi. So I need to find this. All right, so where is that? Well, this guy here is this, which is same as v final, same as vx because it's constant. And here's one equation that I can use, right? So I have one equation that I have for the vx. That means I go and use, okay, so vx is equals to then delta x over t. That's one equation. And I have delta x, right? See, the x final is 90 meters. That means my delta x here is 90 meters. The only problem right now, I don't have the time. Otherwise, I would just plug in there and calculate and done with that. I don't have the time. That means if I have time, I could just calculate this. I have my VIX. Then I can just say that this would have been that, and that's it. Now the question is that then how do I find time? Obviously, I cannot use this delta x equation anymore because, I have two unknowns there. But then you go and look at your vertical direction equations. Remember, the time is the same, right? So then you have equation 1 with the time, 2 with the time, and the 3 with the time. Sorry, 4. Then you say, okay, so which one can I use to find the time? Well, if I look at then these equations, the first one, I can't use it because with unknown time, I also have unknown final velocity. Equation 4 also with unknown time, I have unknown final velocity. But equation 2 is final velocity unknown, independent. That means I only have unknown as time. Everything else is given. And that's the equation I'm going to use. I'm going to say y final equals y initial plus v initial in the y direction times time minus 1/2 gt squared. And good thing here then that this is 0 initial velocity and initial position. And even initial velocity 0 makes the entire term over there 0. And then this is then minus 1/2 gt squared. Then I rearrange where then I have then, so for time, right? I'm sure you guys can do this, rearranging and solving for time. This becomes then 2 times negative 2 times y final divided by g, and then the square root because t is squared. So then this is equals to square root of negative 2 times then negative 50 because y final was negative 50, then divided by 9.8, and I can then find the time. All right. The time in this case is going to be 3.19 seconds. Now that I have time, I can come back. So come back to my previous equation and write the time that I just calculated. Then that means 3.19 seconds here. Calculate my initial velocity component in the x direction. And then I'm going to get 28.2 meter per second. All right, so that's my initial velocity in x. But from the beginning, I learned that initial velocity in x is equals to initial velocity. That means I can say then, all right, then this is also my answer. That means that's also how fast it has to be going initially to make it, 90-meter horizontal displacement where the cameras are. Right, so that's basically the solution for this problem. All right, so let's look at another example here. We have a football that is kicked at an angle of 37 degrees with a velocity of 20 meters per second as shown. So calculate the maximum height, the time travel before the football hits the ground, and how far away it hits the ground, and the velocity vector at the maximum height, and the acceleration vector at the maximum height. All right. So, and we're going to assume that the ball leaves the foot at, the foot at ground level and ignore air resistance and rotation of the ball. Right. Perfect. That means we can treat this as a, a purely two-dimensional free fall problem. Now, for this problem, then you can say what are we given is the initial velocity, which is 20 meters per second, initial launch angle, which is 37 degrees, and it seems like nothing else we're given. Well, we can take this initial position in x and y, set it to 0, and I can say then ax equals 0 and ay equals negative g. All right. I'm going to then separate this motion into like 3 points. I'm going to say point A is the starting point. The highest point here, I'm going to say that this is point B. And when it hits the ground back, I'm going to say that this is point C. Right. Point A, point B, point C. So that means what I want to find here is this. I want to find what is the vertical position of point B, right? Because that's what is the maximum height. Maximum height is that how high you go in a y direction, and then point B is my highest vertical position. So what is y of B? Part, B is asking the time from A to C. Part D is asking, part C is asking what is my x final, right? That means x of C. And then after that, it's asking what is velocity, two-dimensional velocity at B, and then what is acceleration at B. All right. Those are the things that we want to find. All right, so now let's start with part A. Let's calculate the maximum height. Now, before we even do anything, actually, remember, we were given initial velocity and initial launch angle. And clearly this is a different, the second type of problem for a projectile, which the launch angle is not 0. So we have to take the launch angle to be 37 degrees with initial velocity of 20 meters per second. And I use those to find initial velocity in the x direction, which will be v naught cosine theta. So 20 cosine of 37. So I should get 16 meters per second. And then I find v naught in the y direction, which is v naught sine of theta. So then 20 sine of 37. And that gives me 12 meters per second. That means I have my initial velocities in the y and x direction. One thing to remember is that in the velocity in the x direction then will never change. Right? It's always going to remain constant. But velocity in the y direction, so velocity in the x direction never changes, but in the y direction then it's going to change. So right now, as I want to go from, let's say, for part A, I want to go from point A to point B, and I want to find what is basically my delta y, right? What is the y position of B? All right, so then what we do here is we look at our kinematic equation in a y direction, because I have to look at those, let's say equations, right? So basically this equation, right? This set over here, and see which equation can give me that. So equation 2, 3, and 4 have displacement, right? Equation 2, 3, and 4 have displacement. Then I need to know which one I can use, okay? Equation 2 is generally a nice equation to find y final, but equation 2 requires me to know the time, and I don't have the time right now. I can find the time, technically, using equation 1 and then use that, but for now, let's say we don't have the time. equation 3 doesn't need time. Okay, that means I can actually use that, because here's what I have. So equation 2 gives me this. V final, which is technically V at B, equals V initial. That means, let me put it like as Y. V initial is vertical velocity at point A, then this R squared, then minus 2G times delta Y. All right, delta Y is basically going to give me YB because YA is technically 0. See, in this equation, I know one thing, that point B is the highest point, which means any vertical velocity at the highest point, then it's going to be 0. That means this guy here is 0. That means then 0 equals VAY squared minus 2G delta Y can allow me then to find delta Y, which will be then VAY squared divided by 2G. So I can find this and calculate and get this to be 7.4 meters. Okay. Is there anything else I could have done? Yes. I could have used equation 1 to find time it takes to go from A to B, and then use equation 2 to find position, which I have as a solution in the slides. So you can look at it. I'm giving you basically different type of solution. All right. What else then? Part B. Part B is asking, how long does it take for it to go, let's say from A to C? And there are two things we can do. All right. There are two things we can do. One of the things I could do here is, I understand that points A and C are exactly the same. So technically then I can find how long does it take to go from A to B, and then just double that time. And that's probably an easy way to go around. So find the time from A to B, then double that. That's the time from A to C. Or I can just directly go from, say, okay, I'm going from A to C, right? And then use that to find the time. And to do that, I'm going to use equation 2. Final position, which is Y of C, equals initial position, Y of A, then plus initial velocity at A in a Y direction, right, times time, minus 1/2 then GT squared. So I'm going to use this equation to find the time going from A to C. Because here's what I have. I know the position of, vertical position of C, that's 0. And I know vertical position of A, which is also 0. Then this becomes VAY T minus 1/2 GT squared. Then if I rearrange this, then I have 1/2 GT squared equals VAY times T. See, that this doesn't become quadratic equation because I can cancel the time like that. All right, then from here I can solve for time, which will be 2 times VAY divided by G. That means 2 times 12, right? 2 times 12 divided by 9.8. Because this is my VAY, right? Technically, this is my VAY. So then the time will be 2.45 seconds. That's my position, that's the time to go from position A to position C. All right, that's part B. Part C is asking me to find the range, horizontal position change from A to C. Well, remember, there's only one equation for that range, right? It's delta X equals Vx times time. That means going from A to C. And this is the time going from A to C. How about Vx? Do I have that? Well, remember, I calculate V initial X, which is 16. But remember, this is just Vx, right? Because time, the velocity in X direction never changes. That means I can just say, all right, so this is just 16 meters times 2.45 seconds and calculate the range, all right? So which should give me roughly 40, I think 39.2 meters. There you go. All right, that means roughly 40 meters going from A to C in the X direction. And we're about, 7.5 meters in a Y direction at the highest point. All right, so then I have part D, which says, what is the velocity vector at the maximum height? Well, we kind of talked about that, right? So velocity vector at point B is equals to Vx at point B plus Vy at point B, but this guy here is 0. That means there's only x component velocity. And x component velocity is always 16 meters per second. That means that's what I have. That means this velocity vector at point B has a magnitude of 16 meters per second and pointing in a positive x direction. Because it has no y component is 0. Finally, the last one, which is, how about the acceleration at the maximum height? Well, remember, acceleration here is always negative j hat for a free fall, regardless which position I'm talking about. This acceleration is the same at point A, B, C, or any other point that I consider. Because this is acceleration due to gravity, right? And doesn't matter if you're standing or hiding or jumping or swimming, right? This acceleration due to gravity always acting on you. Okay, so don't think like, let's say, if you're at the highest point, your velocity is 0, right? That means there's no acceleration. Remember, acceleration is changing velocity, not just velocity. Okay, that means A equals negative j hat the entire time going from A to C. All right. All right, so here's another example. We have a grasshopper can jump a distance of 30 inches, which is about 0.76 meters, from a standing start. Okay. And I guess the question is this: if the grasshopper takes off at the optimal angle for maximum distance of the jump, what is the initial speed of the jump? Actually, I don't have this question, so you can look at the lecture notes for that. So again, if the grasshopper takes off at the optimal angle, which, remember, we assume that to be 45 degrees, okay, what should be the initial speed of the jump? Now, what we're given here is the range, 0.76 meters, and it seems like nothing else. But we are also told that there's an optimum height, the angle, right, which is 45 degrees. So we want to find, initial velocity, initial speed. Well, we're going to assume that here's a grasshopper starting from point A, and when it jumps, goes from here to there, right, coming back to the ground. That means, let's say that's my point B, this point, right, for this. And then y of A is equals to y of B. If that's the case, then remember I have this one equation that we could have used, which is the range is equals to initial speed square times sine of 2 theta divided by g. We can use this equation. That means I can rearrange this and solve for, let's say, the initial square, which then will be r times g divided by sine of 2 theta, then take the square root. Okay, and I can solve for that. You can see, right, all I need to do here is plug in 0.76 meters times 9.8 meter per second square, then divided by sine of basically 90 degrees, right? 2 times 45 is 90 degrees. Okay, that means for this one, then I can calculate the speed, the initial, so let's say this is part A. So the initial to be 2.7 meters per second. All right, so you can use this equation, but remember, this is the condition. That means for that range, right, you assume that vertical positions are exactly the same. Then you can use this equation. All right, so then the part B says this. Most animals jump at a lower angle than 45. Suppose the grasshopper takes off at 30 degrees from the horizontal. What jump speed is necessary to reach the noted distance? All right, that means what we're doing here is we are calculating the initial speed using basically the same equation, right? R times g over sine of 2 theta, but assuming that this time theta here is not 45, but 30 degrees. That means we still want to see that, we want to have 76 centimeter distance, and we want to have then 30 degrees right now jump. So that basically this is 60 degrees, right? And we're going to see that in order to achieve the same distance, it has to be, jumping at 3.2 meter per second rather than 2.7. That means the initial speed should be faster so that it actually reaches greater distance. All right, so that's basically this part B. All right, so one more example. So this last example in the projectile. So a rescue helicopter wants to drop a package of supplies to an isolated mountain climber on a rocky ridge 200 meters below. If the helicopter is traveling horizontally with a speed of 70 meters per second, how far in advance of the recipient's horizontal distance must the package be dropped? All right, so then let's look at what we have. Now, what type of problem is this? Well, clearly it's a projectile because you drop a package and it's basically in a free fall. Also, what type of projectile problem is this? Well, is it, launch angle 0 or with some launch angle? Well, one thing we have here is this. See, like, let's say initially the helicopter, we are told that is traveling horizontally. That means this is the velocity of the helicopter, which is at 70 meters per second. That means we have initial velocity, of the helicopter, and put like H for the helicopter. And this is basically initial in the X I hat plus initial in a Y J hat. And we are given this as 70 meters per second I hat plus 0 meter per second J hat. And here's what I have. When the package is dropped, package doesn't just go straight down, which sometimes students think that's how it happens. No, when you drop the package, at initial time, it's actually be moving exactly the same way as the helicopter. That means, initial velocity of the package then will also be 7 meters per second I hat plus 0 meter per second J hat. This is how the initial velocity of the package will be also, which means it has no Y component, which means then theta initial here is 0 degrees. It's only moving horizontally. So that's why it's a zero launch angle with no initial velocity component. All right. Pretty much like very similar to the, the motorcycle. So that's why motorcycle, going off a cliff or package dropped by a helicopter, it's exactly same problem. And you're going to see I'm solving it this very similar way. Okay. Just difference here is that I'm given initial velocity. I'm just want something different, which is, basically what should be the, the distance, right? Horizontal distance between the, let's say where the package is dropped and where the island is. Because if you wait and drop it right here where the, if you helicopter is here and then you drop it, well, you're going to miss it. It's actually going to go and, hit the, water somewhere over there. Okay. So it's not going to go straight down. So that's why it's important when you're dropping something, you don't drop it right above where you want it to go because the helicopter is moving initially. If helicopter is, at rest, right here, if it's at rest, then yes, drop it straight down. But if helicopter is moving and you're dropping, you have to drop it some distance X before your, destination, let's say. And that's what we want to do. We want to find basically what is this X. So what is given to us is this. V initial is 70 meters per second. That's the initial velocity vector. Theta initial here is 0. Then Y initial here is 0. Y final then negative 200 meters. Remember, I always take the initial position where the object is launched, right, as 0, and then final ground, which is negative value for that. And we're also given AY equals negative G, AX equals 0. All right, so what we want to find here is basically X final, right? X final. That means this is, what is this displacement? Or if you want to say, you can say, what is this delta X? Like that. All right. So again, what we do here is, you can see, right, when you try to do this, V naught X equals V naught cosine theta, V naught Y equals V naught sine of theta, you're right away going to get this is equals to V naught, this is equals to 0. So that's why V naught X here is 70 meters per second, which means this is our Vx, because that means Vx never going to change, right? If initially it's 70 meters per second, it's always going to be 70 meters per second. Initially in Y direction, there's no velocity because it's a zero launch angle projectile. Okay. Now, how do I find delta X? Well, it's simple. That there's one equation, Vx times time, and I have Vx, 70 meters per second. Well, the only problem is I don't have time. Well, luckily for us, there are equations in the Y direction that can give me that. And you go back and look at which one can give you that, which one, let's say, has time. Remember, we have the height, and we have the acceleration, and we have the initial velocity in the Y direction, which is 0. And one thing we don't have for the y-axis is that the final velocity. That means with what is going to be the speed when it hits the ground? And it's never zero because we're talking about impact speed. Well, lucky for us, there's one equation that doesn't need final velocity. And that's basically this y final equals y initial plus v initial in the y direction times time minus 1/2 gt squared. So y final, so this is zero because v initial is zero, then minus 1/2 gt squared, again rearrange and so forth time, which will be negative 2 times y final over g. And we already did similar thing, right? So then going to be negative 2 times negative 200 meters, so negative is going to cancel out, divided by 9.8, and I'm going to calculate this to be 5.71 seconds. All right, sorry guys, 6.39 seconds. Then I take it and move it here, 6.39 seconds, and I calculate my displacement, which is roughly 450 meters. There you go. And that's what I have for this one.